Hello. In the last few lectures, we have defined Gaussian curvature of a surface. So Gaussian curvature, it captures the bending of the surface away from its tangent plane. Our next goal is to study about geodesics in a surface. So geodesics, locally, it is the shortest length path. So in order to define geodesics in a surface, so we'll first introduce the concept of covariant differentiation of a vector field. So this lecture will be about covariant differentiation about a vector field. So let us begin. Okay, so let us start with a regular surface S in R3. And let us take a surface patch U sigma. Okay. So let me draw a picture. So this is my say surface patch. So this is sigma u is contained in S. All right. So first, we'll define vector field on this open set sigma u. A tangent vector field on sigma u is a correspondence W that assigns to each point P belong to sigma u a vector WP in the tangent space of S. Okay, so this W, it is a map from the sigma u to the union of tangent space of S. So this Q, it belongs to sigma u. So W of P, it is a tangent vector in TPS. Okay. So in the picture, so suppose if I take this point P and I take the tangent plane, So W of P, it will be a vector in this tangent plane. And now if I vary this point P, suppose this P prime is another point here, and I take the tangent plane, and for this P prime, I have another tangent vector W P prime. Okay, so this is my definition of this tangent vector field. So note that, so W of sigma u, it is collection of vectors. So these vectors, it lies in R3. So the vector field W is called differentiable if W compose sigma is a differentiable map from U to R3. So this W compose sigma, it is a map from this U to R3. So if it is differentiable, so then we call this W to be differentiable. So now, if I take any open set, so let G be any open set in S. And W be a tangent vector field on G. So that is, so W, it is a map from this G to union of TQS, Q belong to G. So W is defined in this following way. So W of P is a tangent vector in TPS. Okay. So the vector field W is differentiable if there exists a surface patch U sigma such that whenever sigma U intersection G is non-empty, the map W compose sigma is differentiable. Okay. So we have the notion of this vector field on an open set of a regular surface. All right. So now, next we will define this covariant derivative of a vector field. Okay. Okay. So definition. So let W be a differentiable vector field on an open set U of S, and let us take P belonging to S. So let us take a vector V belongs to TPS. So let alpha be a curve in U with alpha 0 equal to P and alpha prime 0 is equal to the vector V. So let WT, this T, it belongs to the interval minus epsilon to epsilon, be the restriction of the vector field W to the curve alpha. So let me draw a picture. So suppose you have this surface and at each point you have a vector field like this. Suppose this is my open set U in S, and I have this W vector field. Okay. Now, let us take a curve alpha, and for each point of this curve alpha, so I have this vectors. So this is W restricted to alpha. Okay. So this is my, in short, it is WT. So these vectors are my WT. All right. So this W, it is a differentiable vector field. So I can talk about the derivative of this capital W. So this will be a vector in R3. So if I take the derivative of this W, it will be a vector in R3. The vector obtained by the normal projection of dw dt let us take dw dt at the point 0 onto the plane TPS is called the covariant derivative or at P of the vector field W relative to the vector B. Yeah, so suppose this is my point P and suppose uh, so this vector is my dw dt. And after that, so what you do, so take the normal projection of dwt onto the tangent plane. So let me draw the tangent plane. So this is my tangent plane. And for this tangent plane, I also have this unit normal. And then, so what we do, so we have uh, to take the normal projection. Okay. So we have this vector B, which is B is alpha prime 0. So this vector B and take the normal n. So take the plane generated by this B and capital N. So take this plane no, so this is not required. So we have to take this normal projection of dw dt. So what you do, so take the plane generated by capital N and dw dt. Yeah, so take this plane and take the orthogonal projection of this vector on the tangent plane. So take the normal projection. So normal projection means the following. So you take the plane passing through n and dw dt. And take this projection here. So this vector, so this is the covariant derivative of this the this vector field w. So dw dt at 0. So let me write down. So the covariant derivative is denoted by d capital D w dt of 0 or capital D v w at the point P. Okay. So let me explain this thing again. So I have this surface. So suppose this is my open set U in S, and I have this point P, and now you take the tangent plane at the point P. So this is my TPS, and suppose this is my curve alpha. So on this curve alpha, so I have the vector field. So this is my, say, W. So this vector field we have. And for this curve alpha, we have this uh, tangent vector at P. So this is alpha prime 0. So we also have this unit normal to this tangent plane. So this is n or n of P. And now we are taking the derivative of this vector field capital W. So suppose dw dt small dw dt, it will be a vector in R3. So this is evaluated at the point t equals to 0. And so then, uh, so we take the normal projection of this vector dw dt to this tangent plane. So this is my capital dw dt at 0. So capital dw dt, it is the covariant differentiation of this capital W at the point t equals to 0 relative to the vector alpha prime 0, which is equal to v. Okay. So now let us observe this thing. So this above definition, it makes use of the normal vector of S and of a particular curve alpha tangent to the vector v at P. Okay, so this covariant differentiation, so this is a concept of intrinsic geometry, and it does not depend on the choice of the curve alpha. Okay, so let us see why it does not depend upon the curve alpha. So let sigma ut comma vt is equal to alpha t. So this be the expression of the curve alpha, and let capital Wt, so this is equal to At sigma u plus Bt sigma b. So sigma u and sigma b, so these are my tangent vectors of the tangent plane at the point alpha t. So this Wt, it will be a linear combination of this sigma u and sigma b. Now if I take the differentiation, so dw dt, so this will be equal to, so a sigma u u prime t plus sigma u v prime t plus b times sigma u prime t plus sigma, yeah, so one mistake. So it will be sigma v u prime t plus sigma v prime t plus a prime t sigma u plus b prime t sigma b. Okay, so note that this Wt, it is equal to At, the function At sigma u. Now it is also a function, so sigma u of alpha t. So yeah, alpha t, again it is sigma ut comma vt plus bt sigma v of alpha t. Okay, and if I take the derivative, I'll get this expression. Okay. So now, now observe that, so the sigma u, so this was equal to gamma 1, 1, 1. So gamma 1, 1, 1, it was the Christoffel symbols. So sigma u, it is a vector in R3. So sigma u is linear combination of sigma u, sigma b, and the normal vector n. So sigma u, it was gamma 1, 1, 1, sigma u plus sigma 2, gamma 2, 1, 1, sigma b plus L1 times the normal vector. And similarly, we have the expression of sigma u b, sigma b u, and sigma b b. So I'll not write all those things. Okay. So so now note that, so this dw dt, it is the normal projection of dw dt on the tangent space T alpha Ts. Okay. So if I project this sigma u on the tangent plane, so this part, so this L1n part, it will be equal to 0. All right. So since capital dw dt is the component of small dw dt in the tangent plane, so we drop the component, or we drop the normal component in the equations of sigma u, sigma ub, sigma bu, and sigma bb. Okay. So therefore, so what we have, so capital dw dt, so this will be equal to a prime. So a prime means a prime t plus gamma 1, 1, 1, a u prime. Again, u prime means u prime t plus gamma 1, 1, 2, a b prime plus gamma 1, 1, 2, b u prime plus gamma 1, 2, 2, b b prime whole multiplied by sigma u plus b prime plus gamma 2, 1, 1, a u prime plus gamma 2, 1, 2, a b prime plus gamma 2, 1, 2, b u prime plus gamma 2, 2, 2, b b prime whole multiplied by sigma b. So this expression shows that capital dw dt, the covariant derivative, depends only on the vector u prime 0 prime comma v prime 0 prime, so which is equal to the vector v. and it does not depend upon the curve alpha. Okay. Yeah. So let us again recall what we have done. So we have taken this alpha to be sigma ut dt, and this vector field W, it was defined on the whole open set, and restrict this W on this curve. Okay. And we take the derivative with respect to t, and after taking derivative, we take the normal projection. So that normal projection is independent of the curve alpha. This capital dw dt, it only depends upon the vector alpha prime 0, which is equal to b. So this dw dt depends only on the vector. Yeah, so this should be d sigma at the point P, u prime 0, v 0, which is equal to b. Okay, so this p, it is just alpha prime 0. So it depends only on the vector b. So you can have another curve beta such that beta prime 0 is equal to b. But this capital dw dt at t equals to 0, it only depends upon the vector b. So not upon the curve alpha and beta. Okay, so I'll stop here.